Hey guys, welcome to my channel QED. This is going to be my very first video, very first upload in this channel. My goal is to create a series of lessons starting from the very beginnings of graph theory all the way to the most complex and intricate algorithms and proofs in graph theory, such as the five-color theorem, four-color theorem, maybe even Prim's algorithm. So that being said, um, let's get started on the origins of graph theory. So the problem which sort of inspired graph theory, the thing that every subject in mathematics has sort of an origin. There's a problem that was envisioned in real life that needed a solution, and that brought rise to mathematical concept. This is how pi was created. This is how things like Euler's number was created, and this is how graph theory was also created. And the problem that is mostly credited for the creation of graph theory is the seven bridges of Königsberg. Hopefully, I did not butcher that name, but it is a city in back then Germany, now modern day Russia. And the city looked like this, as you can see on the map. It was like a bunch of islands put together with a couple of bridges. These green looking things are supposed to be bridges of the city, which connects the land masses together to allowing people to cross over the rivers. And a question arose in the city. The question was, is there a way for one person to go between each of these islands and go and cross every single one of these bridges in a way where you do not have to cross the same bridge twice? And this was the question that was given, and Euler came up with the proof which said, absolutely not. There is no way that you can cross every single one of these bridges without having crossed at least one bridge more than once. And you can play around with this. If we start off at this bridge, we can go across to the other island and we can come back to the same bridge. It doesn't matter where you go. Let's say you go down to the bridge on the right. If you go up, well, now you can't take this two bridges because you've already went through them. If you go down, well then fine, you can go through this bridge, but now you're stuck again because you've went through all these bridges already. So graph theory was sort of created in Euler's mind to redefine this problem in a way where he can actually prove it mathematically. Now, I'm not going to prove the seven bridges of Königsberg today, but I do want to use this as a base to introduce you to the way graphs are created and essentially the structure of graph theory. So to solve the Königsberg problem, the seven bridges problem, Euler had to basically simplify this complicated looking city into very basic structural mathematical language, mathematical syntax or form. So that's what we're going to do now. We're going to try and simplify this problem. And a couple things we're going to notice immediately is we don't really care how the city of Königsberg looks like. We really don't. All we care about is that there are four land masses and seven bridges which connect these land masses together. So immediately you might think, well, we can just label the land masses. There's one, the landmass at the top, two, the island in the middle, the landmass at the bottom, three, and this other island on our right. So we have four landmasses and we're going to have seven bridges connecting them. And we can easily draw this in a way where we can ignore the actual landmass. We can say that we have landmass 1, which is connected to landmass 2, which is also connected to landmass 3, and landmass 4 here. And we can draw lines between these landmasses which represent the seven bridges. So there's two landmasses, or two bridges, sorry, connecting landmass 1 and 2, 2 between 2 and 3, and 1 between 2 and 4, 1 between 1 and 4, and 1 between 3 and 4. So we've simplified this map of Königsberg into numbers and lines. And we can go even further than this. In fact, we really don't care what the land masses are. It doesn't matter to us that this is landmass 1. We just know that there is a landmass which has this relationship with the other landmasses. We really don't care for our problem where this landmass is. So we're going to get rid of all the landmass labels, and we're just going to assume that we just have a landmass. So I'm just going to draw circles which are going to represent landmasses. And in graph theory, we call these nodes. And interchangeably, you might also see people call them vertices. And the lines which connect nodes together or vertices together are called edges. And I'm not going to get into all the definitions of graph theory, but these are concepts and things that I'm going to be repeating over and over. And these are the basic definitions and basic structure of graph theory. We have nodes, which are represented by dots or circles, and we have edges, which connect nodes together. So we essentially simplify the Königsberg seven bridges problem into a bunch of circles and lines, which is kind of cool if you think about it. And at this point, I'm not going to prove the seven bridges Königsberg problem to be unsolvable like Euler did, but I do want to give you the intuition and thoughts behind how Euler came up with his proof of this particular problem. So one thing that we're going to have to notice about the seven bridges problem is if we want to go to every bridge only once, that means that when we cross one bridge, there has to be another bridge on whichever island or landmass we're on that isn't the one we just crossed, right? So in other words, there has to be at least two bridges for every landmass. If there's only one bridge to a landmass, then you have to take that same bridge back. There has to be at least two. Now, if there's two, then what happens if there was four? Well, if there's four, there's a way to go back and forth. The problem happens is when there's an odd number of bridges connected to a landmass. Because if you look at landmass 1, as soon as you cross this bridge into landmass 1, for example, let me do it in red so it's easier to see. So if we cross this bridge into landmass 1, we can no longer take that bridge. We have to take a different bridge. For example, this bridge back to landmass 2. Now, if you think about it, if you look at landmass 1, we have a scenario where we have this landmass or node where there's only one edge going to that node. Because you can think about it, as soon as you go over a bridge, that bridge is no longer accessible. It's as if there is no edge between those two nodes. So we can redraw this graph and we can remove these two edges. It's as if you're solving this problem now. As soon as you visit these two bridges, now you're solving the same problem with 5 bridges and the same number of nodes. And now you can easily tell that this is impossible to solve. Why? Because as soon as you cross this bridge, which goes to landmass 1, you're done. You're stuck. There's no way back. And if by thinking of the problem this way, you can see that there is a relationship between the number of edges coming out of the vertices and the solution to this problem. And the key point that Euler brought up was that because there are an odd number of edges connected to each of these vertices is the reason, essentially the main reason why this seven bridges problem is not solvable, and uses that concept in this proof. And we will get to a point where we will definitely prove this very soon. Graph theory moves very quick, and hopefully it won't take too long to get to that point. And that's it for this video. I just wanted a brief introduction to graph theory, the motivations, the problems behind graph theory. I think the very unique part about graph theory, the reason I love it so much, is because how visual it is, how the problems really sort of represent real life. And hopefully once we get to later more complex concepts, I can show you some very interesting and cool computer science algorithms that depend and use graph theory and the various theorems on graph theory to do very, very cool things. That being said, thanks for watching, and I'll see you in the next one.